Hey everyone, welcome back to the fourth part of the Tic-Tac-Toe project tutorial. So in this video we'll be taking a look at what Minimax algorithm is and how we'll be using it in our project. So a little bit about Minimax. It's an algorithm that's generally used in game theory, AI, and other such fields. So let's take an example, Tic-Tac-Toe, where the computer was the X. So let's just say the computer started with this position, the center position, and then the human went at this position. Then the computer put an X over here, so the human put a O over here, and now the computer has to decide where to put an X. Ideally speaking, the computer should put an X in this bottom center position to stop the human from winning. So how does it make that? Before we go too deep, let's assume that according to the computer, this entire board at this current stage is a single state for the computer. So we just don't know yet what to call the state. So let's just assume this big blue circle represents it. And just don't mind the crappy animations. Anyways, so let's just say that from that possible state, from this state of the tic-tac-toe board, we have four possibilities. One, two, three, 4, 5 possibilities. But for the sake of convenience, I could not draw a lot more. So let's just assume there are four possibilities. And from each of those four possibilities, maybe you had three more possibilities, so and so and so. So if the computer plays a move which is represented in the blue, then the human would play a move that's represented in white, so on and so forth. So let's say that each move at the end has a number fixed to it, and that number says what is the state of the game. You don't need to worry about what or how the states map to each other. That's not relevant right now. So the only thing that you need to keep in mind is that the computer over here would be the minimizing player and the human would be the maximizing player. That would kind of mean or translate to that the human, the white block over here, is always trying to get the maximum possible number. The bigger the number on a given state, the more favorable it is for a human. That means the human is more likely to win on this than on, say, 1, 3, or 6. Similarly for the computer, if it's the lower the better. So let's say if the computer is thinking from this point, so it knows that the human would always try to maximize its chances. So it knows that the computer would always pick the biggest number, which is 9. And from the second possibility, if this were the way the computer went, the human would always take 6 because that's the maximum and that's what the human wants. Similarly here, it would take 4 from 4, 0, and 1, and from here it would take 5 from 5, 2, and -5. So the computer now knows that among its four possible paths, this is what the human would do ideally or in the best case scenario. So the computer, the Minimax algorithm, if you will, would choose the least of these possibilities because it is always supposed to choose the least amount, and that would be 4 in this case. So it chooses 4. Now if you can imagine, this would be part of a bigger tree where this big blue 4 is just like a very deep down child node for some even bigger tree. Depends on the depth where the computer is figuring all of this out. So you get a rough idea of what Minimax is doing under the hood. It's just the computer going through all of the possible paths and trying to find out which would be the best possible path for it. And this is just a pseudocode. It's not really great pseudocode. It's just mild effort at best. So I did not put much effort into this, but you get the point. This is what we'll be defining. This is not the actual function. We'll be implementing a lot more stuff. So this is def minimax. We give it a board. We give it a depth. Now the depth that we give is how deep should the computer actually go. So that, do I need to think 5 steps ahead? Do I need to think 9 steps ahead? Do I need to think 1 step ahead? That's what it is. And if the depth is 0, or if any one of them has won the game, then it doesn't matter. Just return evaluate board and you say who has won. And we would say best score. We start with the initialization of best score being plus infinity or negative infinity, depending on the player, of course. And then we have our logic where we take the current score from the minimax, and then we recursively call minimax at the lower depth. So we call minimax at the, say, 6th depth, and then we'll say, okay, now from these possibilities for each one of those 6, check all of their 5 possibilities. So you can imagine the recursive tree going increasingly big real fast. It's kind of like exponential almost. But since it's tic-tac-toe, it won't affect our runtime. So let's just get out of here and let's get back to coding. So what we have here, and from what we've coded till now, you should be able to see that we have our win done, we have our player computer done. So what we need to do is implement a couple of new functions. One of them would be called evaluate, and let's just give it the board, and what we'll say is if win of board and it's the comp, if the computer is winning, then we'd give it a score of -1. We'll assign it a score of -1. What do we assign? We assign the board the score of -1. Win board of human. Got an error here. Yeah. Else, why is it showing up like that? Yeah, much better. And then the score would be +1, and if none of them have 1 till now, okay, my bad, I need to say elif, don't know what I'm thinking here, but yeah, else, and then we'll get score equals 0. So there you have it. That's the evaluate board. And one more thing, what we need to do now is actually go back to our roll function, good old isEmpty, and we're going to change it just so that it's much more better for us now to a different name. If you recall from the minimax function, we don't have an empty. We will now be calling it a get depth because that's technically what it's doing. So yeah, just do refactor. There we have it. So wherever we used isEmpty before gets refactored to get depth. So what we do now is we check if there is a 0 in the board, and every time there is, we will increase the variable depth by 1. So let's just declare a depth variable here at 0, and we'll increment it by 1 every time. Once we're done, we'll return depth. Now since we're returning depth, because last time we used to return a true value here, and now we're returning depth, that might not sit well with some previous conditions, especially this one, because we just said here while get depth true. Technically this would work since 1 is greater than 0. Since 1 is translated as true and 0 is translated as false, but this wouldn't hurt it either. So we have get depth done, we have evaluate done. So let's go ahead and actually implement our main function, which is the minimax. We have board, and we will need the depth and the player. So we have our player done. Now what you need to keep in mind while you're implementing this is the fact that whenever you are implementing this, you have to implement it while keeping in mind who the first player goes. If you are implementing it in a different way than I am, otherwise it doesn't matter which player goes first. So let's just we'll have an if condition here that says if player is comp, then we would give a best x of -1, best y of -1, and a best score of positive infinity. Now if you kind of like don't understand what the hell is going on here and why am I writing this, don't worry. What I'm doing here is just the fact that I'm checking whether the player is computer or a human. And if you remember from top here, we gave human +1. We used +1 as a sign, a number, a condition, whatever you might want to call it, and computer as -1. So what it means is human is the maximizing player for us and computer is the minimizing player. And I'm importing infinity over here. So let me just get that. Yeah. Since human is the maximizing player for us, whenever we start with the human, if we start with the human, if our code starts with human, the initial values that you start will be the worst possible values, because it needs to go from that worst to the best possibility. So for it, since the human needs to maximize stuff, its initial properties will be the worst. In this scenario, best score for the human will be negative infinity. Conversely, for the computer, who needs to have a minimal value, so we give it positive infinity or plus infinity, and these are just coordinates to our board. And since we only have a two-dimensional array, we don't have -1, and that's what we give them. Basically, they're invalid values for now. You should not put 0 over there, because 0, 0 is an actual value in our board. So we just do another check here. If depth equals 0, or win of board of human, or win of board of comp, then if either they are winning or if the board has run out, which means it would be a draw, then we just return a -1, and we return an evaluate board. So if it's not the best case scenario, the computer will always try to go for a draw instead of letting you win that way. And now on to the main logic which we have for the Minimax. Let me just scroll down, and yeah, for I in range 3, because for each cell range 3. Okay, why is it highlighted? Never mind. If board of I and the board of J are equal to 0, then what we're doing is, at first we blindly just assign the value to the whatever the player's value is. Like if it's the human or the computer, it doesn't matter for us now. And then what we'll do is we'll try calling the Minimax function on that. Like assuming if the player played that value, how would the Minimax go? Or what would be the future we're trying to predict over here? Damn it, what's wrong? Minimax, and we get the board, and then we get a depth -1, because here we passed in depth, so we are now decreasing depth. We're going one step lower, and now what we'll do, hold on. And now what we'll do is we'll call from the negative player, because you need to keep in mind, once the computer is done choosing its point, what it'll now try to do is try to think as what a human would do in its best case scenario. So the computer needs to think from both point of view, from its point of view as well as yours. So if it was human, the starting one was computer, passed over here, which would be -1, then when it's calling the Minimax on one less depth, it is keeping in mind that it's now your turn, and now the player would be +1, -1 +1, which would be human. And that's how it all gets keep calling again and again and again. That's recursion basically. So now what we can do is, once the entire recursion comes back, and from that we obtain the best possible current score, we set it back to 0 so that it was never changed by us. And then what we do is we say current I and the current J are the I and J, whatever I and J we're currently dealing with. What is wrong with you? Never mind. Guess my PyCharm is hanging for some reason. Yeah, and while you're in this if indentation, all of this needs to be in the same if block. Inside here we take another condition. We say player equals comp, and then we say if not this, if we say current score is less than the best score, because since the computer needs to minimize it, we say if the current score is less than the best score, then we need to make some changes. The best score will now become the current score, and the best X will now become the current I, and the best Y will now become the current J. Now, similarly, we will now have an outer else, and then we'll say if C, or current score. Now if you will recall, the second if condition that we're using here is supposed to be for the human. My bad. supposed to be for the human. This else condition right here, it's supposed to be for the human. The above one is for the computer and this is for the human. We say best score equals current score, and we say best x is equal to current I, and we say best y equals current j. So with that, we have our minimax function all completely done. All we need to do is now return the best x, the best y, and the best score. Now if you will notice here why we never managed or bothered to take the best x or best y is because we are not concerned with how what the variables are or what the coordinates are of the lowermost choices it chose, because down the line the player may or may not choose what the computer predicted. So the only thing that we need, had a semicolon here by mistake, so the only thing we need to focus on is the current score, because the player may or may not pick those. So having the coordinates taken is kind of useless, so that's why we used underscore over here. And that's it. Why is the best x be this local variable best x might be referenced before assignment? Why is that? You didn't say that for best y. Hold on, am I making a mistake here? Nope, I'm not. Best score, saying the same thing for best score as well. Did I not do that up there? Best x, best y. Oh, yeah. I don't think it's anything to worry about. Maybe my Python is just a bit so we probably should stop the video here, or we could, you know what, let's just add the minimax into the computer turn in the next video. We're already 15 minutes ahead, and we should not make this many long videos. Anyways, I'll see you guys next time.